something to look forward to. Huh?
Oh, yes. Well, I got to do a little talking first.
I know you do.
Okay. So, hello. Today we are going to be looking at inverse functions. Once we started functions, we never leave them, okay? Well, except for the last assignment, okay? First of all, let's review what a function is. We said a function was a rule that assigned to each x value exactly one y value. Then we looked at ordered pairs and said, okay, so for a list of ordered pairs, for it to be a function, there can be no repeated x values. And we had a way of looking at a graph and deciding is it a function or not, and it was the vertical line test.
Do y'all remember the vertical line test?
If a vertical line intersects the graph in 2 or more points, it's not a function.
Go back, show them. We had some pictures of the vertical line test.
When
we started functions. We're doing a lot of good stuff.
I know. Oh, look, are slanted lines functions? Yes, they're always. Oh, look right here.
One.
Here was a parabola opening to the right, and it's not a function. If you look at the vertical lines, you can draw vertical lines that intersect the graph twice. So not a function. Where slanted lines are functions. Now, absolute value graphs, the V's, those are functions, provided they're not opening left or right. At this point, we're looking only at stuff opening up and down because those are functions. Like a parabola that opens up, it's a function. It passes the vertical line test. But what about, I'm going to define a new term for us, one-to-one. Something is one-to-one if there are no repeated y values.
Before now, we've been saying it's fine to have repeated y's, you just can't have repeated x's. But if your function's going to be one-to-one, you have the added restriction of no repeated y's.
The key to any IQ test, if you look at any IQ test, it involves patterns. Okay? So I'm wondering if y'all can figure out what I'm going to write right here based on the pattern. I said function, no repeated x value. One-to-one, I changed the x to y. So in purple, underneath this, looking at the pattern, what am I going to write? Not vertical, but horizontal. There's a horizontal test, line test, that you can use to decide if something's one-to-one. Now, demonstrate that in right now. Here's a question. We said that parabolas are, if they're opening up and down, or where did I put my little, I lost that page.
Oh, so you're going to do something else.
We said that parabolas opening up and down, those are functions. Are they one-to-one? Here's the question. Are quadratic functions, in other words, vertical parabolas? So they're opening up or down. One-to-one. And to answer this, I'm just going to sort of draw a generic quadratic function that's opening, and let's see, I think I'll use
at the vertex below the x.
So open it up.
Open it up.
Okay. Let's suppose we have a quadratic function opening up. The question is, are quadratic functions 1 to 1? Well, 1 to 1 means no repeated y values. And I wrote this horizontal line test. What am I trying to say? Like, look right here at the x-axis. Do we have repeated y values right there? Look at this point and this point. What's this y value right here? All we know is that it's the x-axis and y-axis. We don't know the x-coordinate, but we know
it's positive. I mean, negative.
Negative. But what about the y-coordinate? What's the y-coordinate here? They're both 0. So is it 1 to 1? No. There's repeated y values.
Parentheses,
Right there.
negative 0 and positive 0.
Okay. It's like right here. Ooh. I was just going to use the red to put the dot. There. Like right here, this one, negative
X, and the y value is 0.
Positive x, y value 0. Can y'all find more points where there's 2 points with the same y
Anywhere
coordinate?
you can draw a horizontal axis, a horizontal line to hit the graph in 2 spots, it is not 1 to 1. They have the same y value.
So what are we going to answer for this question? Are quadratic functions 1 to 1? No. Okay. Let's go ahead and write out. If you can draw a horizontal line that intersects the graph of a function, and this is true even if it isn't a function. Two or more times the graph is not 1 to 1. Just like if a vertical line intersects a function more than once, not 1 to 1. So we've graphed something else we've graphed real quickly. Here's one question. What about slanted lines? Are slanted lines 1 to 1? Just draw
any slanted line.
I'm just going to do it right here. I'm just going to draw a generic slanted line there. Are slanted lines 1 to 1? If we started drawing horizontal lines, how many times are they going to hit it? Only once. So what about this yes/no question? Are slanted lines 1 to 1?
Remember, we said slanted lines are always functions. We can be more specific now. They're always 1 to 1 function. There's no repeated x and there's no repeated y.
If someone said, say something algebraic, what he just said. Slanted lines are functions, but they are not 1 to 1.
Yes, they are 1 to 1.
But yes, slanted lines are functions and they are 1 to 1. Quadratic functions, that's what I was thinking,
are not 1 to 1.
They're functions, but not 1 to 1. Okay? It's time to start doing a problem from the homework before we get kicked out.
I pulled it up a moment ago. It's a yes/no question. Is this 1 to 1? Yes.
It's a slanted. So I've already. Let me go ahead. Right here where it says example. Oh, where I wrote EX, I didn't realize that was problem 1. There. That's problem 1. Are slanted lines 1 to 1?
Yes.
Number 2 should be a little bit more. What should be a quadrant? Oh. Okay, here on problem 2, you're using the horizontal line test. Now I remember in the past I've had students tell me, oh, they can tell that it's about to turn around. It's a parabola. No, it's not a parabola. Look only at what's drawn there. Pop that out, Tim.
This thing is continuing. It's rising slowly.
Or it stopped.
Or it just stopped. It's just
Don't
stopped.
assume it continues. I remember the student. Oh, it was going to turn around. So they answered no. And I was like, no, just look at the blue curve. Tim,
is that 1 to 1? Yes. You can draw all the horizontal lines you want to. You'll never intersect more than just one.
And you don't need to draw them. They're already there. All those little grid lines, you see?
Yeah.
None of the horizontal lines intersect it more than once. Don't assume it's going to turn around. So that one's 1 to 1. They can't all be that easy. Okay, now I need to define the word inverse. Tim, give me this. The name of this assignment is inverse function. So an inverse is formed by switching or reversing, switching the x values and the y values.
I say swapping.
Oh, maybe swapping would have been better, but I think we're just arguing synonyms.
We're arguing semantics.
Okay. For instance, let's suppose we have this function. I'm writing out a little function. Let's see. 2, 4, 3, 9, 4, 16, 5, 25, 6, 36. And I've labeled this as f, so it's a function, and hopefully you agree it's a function. There's none of the x values are being repeated. Remember we said with functions you can have no repeated x values. Okay? With the inverse, you're just going to, this little notation, it looks like a little -1. You read that as f, and that little -1 there is read as inverse. That's the little notation for inverse. I think I'm making it worse, ain't I? I'm trying to say that little -1 there. Don't read it as I'm saying it. Don't read it f to the -1 or f to -1. Read it as f inverse. So just go right on through and just swap, however you want to word it, the x and y values. Inverse switches or swaps the x and y values. Okay? I think problem number 3 is going to be something similar to this. And it's one that you might be able to do without writing anything down. It says, decide whether the given functions are inverses. Are they going through switching those x and y values? Look really close.
-5, 0. Swapping them, it comes 0, -5. I agree there. What about the second row? Yeah, that's okay. The third row? Yes. The fourth? Everything is swapped, so yes, they are inverses.
Now this is one of those times when just because I'm yes doesn't mean when you do it, your number 3 is going to be yes. Sometimes they have it written in a little bit to switch them.
What do y'all think about this one?
Guess?
Yes, let's look. -3, -4, yes. 1, 3, yeah. Okay, this is another yes, but I'll warn you, the program does periodically, take a positive and make it negative. So for yours, it may say 3, -3, and down here, It's -3, so your answer would be no.
I should have looked through. I wanted one to say, oh, Tim, say final check. You know what? Do a similar question. Let's see if it'll switch it to where it's, oh, okay.
Oh, you want me to do a similar question?
Mm-hmm. Let's see about this one. I guess
No, this is another yes.
yes. Oh, well. Okay, but they do occasionally switch it. No, it's a different type of problem completely. Oh, I like this one. I'm going to write it down. Problem number 5 says, if the following defines a one-to-one function, find its inverse. So here's the, let me see, -16, -9, 14, -13, and 17, 12. There's an if part of this problem. I think 5, 6, 7 are going to be similar to these. And that if part, a lot of times students ignore that. It doesn't just say find the inverse. It says if it's one-to-one, find the inverse. So you're going to be switching the x and y only if it's one-to-one. So let's answer that inverse, one-to-one first.
Is this thing one-to-one?
Oh, Tim, show my paper.
Well, I wanted to look and see the neat writing, and they say, yes, it is one-to-one.
How do we know it's one-to-one? There are no repeated y values. -9, -13, and 12. So it is one-to-one. So, to find the inverse, you just swap them. And so, which one is it? A, B, C, or D? It's a multiple choice. It's A, -9, -16, -13, 14, 12, 17. Okay. Now, if any of the y values had been repeated, you would have chosen D. Okay. I suspect before we're finished, we'll have some like that. Problem number 6. Oh, this is a tricky one. -10, -7, -5, -7, and 6, 19. The instructions say, if it's one-to-one, find the inverse. So, in plain English, it's saying, if there's no repeated y values, switch the x and y. Is it one-to-one? No. Why? -7. Same. I'll just say repeated. Y. Repeated y.
The reason we're only interested in inverses that are functions. If it's not one-to-one, when you reverse these ordered pairs, those repeated y's are about to become what? If you swap them, they become repeated x's. Look at this inverse that Tony's finding.
See, I'm finding the inverse, which is not the correct answer on there. The instruction said, if it's one-to-one, find the inverse. Going back to something I said earlier, we're only interested in functions.
Maybe you should write out the way I write it out. Only one-to-one functions have inverses.
You're getting ahead of me. I was going to write this out. And,
no, okay.
So the question, why is the answer, if you look at the answer, punch in the answer to that problem. Not one-to-one. I remember years ago having that on a test. Everyone in the class missed it. You know what I did? I went back to my test for the next semester. I removed that problem. I thought it was an easy problem. What do you think the wrong answer was that everyone in the class chose? A, B, or C?
C.
C? They just saw the last part. find the inverse. That's not what the instructions say. Now, why is it? Well, if we only want functions from now on, this would be wrong because it's not a function. If there are repeated y values, then when you flip them or switch them, there's going to be repeated x's. So, as my brother was saying, only one-to-one functions have inverses that are functions. In other words, if function f has repeated y values, its inverse is not a function because it has repeated x values. So, if there's repeated y's, oh wow, that looks so messy. You can tell I didn't win a penmanship. Right? If there's repeated y values, then when you switch them, you have repeated x values, which means it's not a function. Only one-to-one functions have inverses that are functions. In other words, if there's repeated y's in f, then the inverse has repeated x's. And we're only interested in one-to-one functions from here on. Okay? Let's see. Number 7. Number 7. Oh, here's another one. Okay. Number 7. If the following defines a... Oh, it's the same instructions. If it's one-to-one, find the inverse. If it's not one-to-one, write not one-to-one. Or in other words, choose D. Is the answer going to be D on this one? Is it? Number 7, let's see. Let me write it down. -4, -9, 32, 9, -8, -1, -9, -7. So it's asking, is it one-to-one?
Yes.
Yes.
Every y value is different.
No repeated y's. So, what's its inverse going to be? You know, just go through and switch the x's and y's. Notice how you now have a function. So what was it? A, B, C, or D?
I think the C. 4.
Oh. Okay. Any questions so far? Oh, this is a good one.
Maybe you should use that example you just did.
I think that's a brilliant idea, Tim.
That's what I would.
Look at this. The set of x values, that's called the domain. You know what? I'm going to introduce the f and f inverse notation here. On number 7, I'll call this first one the original function f. Down here where I switched when I switch the x and y, that's labeled f. Remember the little -1 is inverse. So let's start off writing the domain of f. Suppose someone said, write out the domain of f. Remember, those are the x values. So to write out the domain of f, we'd have -4, 32, negative 8, and negative 9. Is that the domain of F? Now let's find the range of F. The range of F would be the y values, negative 9, 9, negative 1, negative 7, and now I should have written smaller.
What's the domain of F inverse?
I'll ask it. Which one of these is also the domain of F inverse? I already have them written out here. This,
The range. The way we're swapping the X's and the Y's. Go ahead.
the X became a Y, the Y became an X. The domain of F is also the range of F inverse. Why is that? Hopefully it's clear why. This is just a lot of terminology. The X value became a Y value. In other words, domain became range. Range, the Y value became, what am I about to write right here? Domain of F inverse. So it's the way we're switching the X and Y. Okay.
Now look at what number 8 says.
And show them the options.
The domain of F is equal to the blank of F inverse. Which one am I choosing? The range.
In other words, X became a Y.
The
Now-
range is equal to the
Domain. The Y became an X.
And that should be obvious because the way you're creating that
Switching the
inverse.
X and
You're
Y.
swapping the X and the Y.
The domain became the range became the domain. Let's see, which one was that we just did? Oh, number 9.
Number 8.
We
Now
just did
number
8.
9.
Now we're going to do number 9. Okay, number 9. It says, fill in the blank. A function has an inverse, and here's the statement. F of negative 3 equals 6. Ooh, this might be the hardest one we've done this semester. I like the way you put it away before I finish writing it all out, because I think that maybe they do too much there on that one. When you're working with function notation, the number in the parentheses is the X, and your answer is the Y. When I'm working with an inverse, how am I going to do that? What am I going to put right here? Do I put the X or the Y? The Y, yeah. 6, and go ahead and let them see. That's what it said, right?
Mm-hmm.
Okay, so you have F of negative 3 equals 6. That means F inverse of 6 equals, what number are you going to put in that blank?
Write out the ordered pairs that are being generated.
Okay, good
Write out the
thinking,
ordered
Tim.
pairs that this first statement generated.
So here's this ordered pair. X, Y. We know with the inverse, it should be swapped to 6 negative 3, is it? Yeah. Okay. So F inverse of 3 equals 6 means, no, F of negative 3 equals 6 means F inverse of 6 is negative 3. Here's something. I think everyone's 8 and 9 is exactly the same. Okay. I mean, they may have maybe they changed the numbers on it or not.
Let's see. Try it again.
No. See, they don't even
Look at
change
that.
the
They
numbers.
don't even change the numbers.
So everyone's 8 and 9 is the same. And Tim, this is where we switched last semester. Is this where you want to switch now?
Okay, I better go ahead and switch.
Oh, okay. I can tell you're just sitting there bursting, wanting to talk.
I'm not sure you're saying it the way I would say it.
Oh,
Hold on.
I'm going to turn this on.
Oh, wow. We were doing these. Yeah, I'm on the hiring committee, and I can tell y'all this. I'm not violating any confidentiality or anything. But someone, I'm not going to call who, had the great idea that for all the faculty, we get in one room and then do this little Teams interview with the candidates. Everyone had to have their own computer and microphone. What do y'all think happened? Scream! It was just a nightmare. After the first one, I said, we need to split up. I thought we were going to all meet in here with one camera and interview the candidates.
Yeah, we could. I mean, all these things have the webcams.
Yeah,
and
that's
so,
what I thought we were going to do. But no, everyone had a different, like if all of us were doing a little, what's the other thing called, like Teams, Zoom or something?
Zoom.
Everyone with their microphones on in the same room, you know there's a lot of feedback. And so I'm thinking I want to turn on my microphone and just see if I can get yours to mess
and
up.
now I'm trying to remember, what are we doing now?
Okay. Tim, you hit 62 and
No.
oh gosh, Tim, the memory's the first thing to go.
I can tell you right now that ain't true.
Unless you forgot.
No joint pain was the first thing, okay. Arthritis set in, that was the thing. You see me moving my hand, it's arthritis, believe
So
it or
weird.
not.
When my mother passed away, she had big old arthritis joints in her finger. I swear, within a month.
Mine was the next day. I was like, what is this lump here on my finger?
They
That's
thought
this big
she
lump
passed
on my
away
finger.
and passed
Passed it.
arthritis. I just want y'all to have something to look forward to. And you
Okay.
sit there thinking, that's so far away. It'll get here, trust me.
Okay.
Oh my gosh, it's being recorded. Be
We
quiet.
need to look at the formal definition of the inverse function.
Because what did I say? A switch, the X and Y.
That's not a very formal algebraic definition, okay? Let's assume that DEF is the definition. Assume F and G are one-to-one functions. F and G are inverses. If each of the following is true. There are two conditions. The first one, F composed with the G of X is equal to X for every X in the domain of G. So if you find their composition, remember doing that? Was that the last time? Or the time? No, the last time was zeros. 1 week ago, we were finding compositions. If the composition at X reduces just to X, and if you reverse the order of those functions, G composed with F of X also reduces to X for every X in the domain of F. There were some problems in our homework that we were doing 1 week ago today. They're at the end of the assignment. Do y'all remember that? You had to find, in both cases, the answers were XX, yes. The compositions were equal, and everything canceled out except for X. And I remember telling y'all, in a week's time, we'll be looking at this. I'll be reminding you of this. Where is it? There. Oh, that really looks messy. How about this one? This one's neater. Do y'all remember that? They gave us two functions. We found their compositions, and in both cases, everything canceled out except for X.
And so, yes, their compositions were equal. And I said that we'd get to a point where we'd be calling those functions inverse functions, and we're now at that point. Well, you know something? How is this equivalent to saying that reversing the x's and the y's will give you the inverse? I don't know that this is necessarily obvious. Think about, let's look at this one-to-one mapping that I'm about to draw. Let's suppose f takes 1 to 3 and 2 to 4. That's function f. Now intuitively we know that if we're looking at an inverse, the inverse must take 3 back to what? 1. And 4 has to go back to 2. So what this function is saying, it doesn't matter the order in which you perform the functions. Wherever you start, perform the two functions, you're going to end up where you started. So if I start here at this 4, 4 goes to 2, 2 goes back to 4. If that always happens, where you start is the place you end. The only way that's going to happen is if the ordered pairs are just reversed. In this case, f and g are inverses. But compare that. Suppose the ordered pairs weren't just swapped. Would this be true? I'll let f take 1 to 3 and 2 to 4. But suppose g didn't go back to the, just reverse the ordered pairs. Suppose g took 4 to 1 and 3 went to 2. Perform the two. Let's just start here at 4. 4 goes to 1. Where does 1 go? To 3. You don't end where you started. That means these are not inverses. This notation is saying no matter where you start, when you perform the two functions consecutively, you'll end up where you started. And that only way that happens is if the x's and y's are just swapped. Let's look at, but now we have an algebraic method. You give me two equations, function equations, and I can decide if they're inverses. Because I know how to find their compositions. So if everything reduces to x in both directions, great, they're inverses. If there's stuff that doesn't cancel out and you're left with something other than just x in both directions, then your functions are not inverses. Let's look at number, is it 10? Here they give us two function equations. Looking for the pizza and pineapple picture for Fog and Golf. Do you remember that? I remember it. Yeah. I can't find it on the It's phone. In there somewhere. I thought it was on the. I thought it was on the hard drive. Oh, on the hard drive. I can't look at that while you're doing it. Do y'all see that this idea of switching ordered pairs isn't quite so obvious? When they list out the ordered pairs, it's easy. But when it's written like this, it's not quite so obvious anymore. That's why you need something. How you can look at the equations, those little formulas, and decide, are they inverses? Let's find f composed with x, fog x. F composed with g. I mean, f composed with g. What did I say? F composed with g. Now, remember how we do that. G of x is the inner function. You take g of x and you plug it in for x in f.
So we have that 3 over. We're going to have to replace that black x with this messy stuff here. The 3 over x plus 8. What else have I got stuck on down there? The minus 8. Okay. This is a compound fraction, a fraction that contains additional fractions. Now, if these things are functions, or inverses, everything except blank is going to cancel out. I think the 8s are about to disappear, aren't they? 8 minus 8, that's gone. So we have 3 over the fraction 3 over x. These are called compound fractions, a fraction that contains one or more additional fractions. This big fraction bar, that's the major fraction bar. Any other remaining fractions that appear, they're the minor fractions. My approach to simplify this, if you've worked with these before, then you may have a different way of reducing them. But what I like to do, I look at that minor denominator. If there were more than one minor denominator, I'd find the least common denominator. But in this case, there's only one. I'm going to multiply above and below by that minor denominator. You can multiply above and below by anything you want to, and the fraction maintains its equality as long as you don't multiply above and below by 0. So, multiply by x, multiply by x. This is working out really nice. We have a 3x on top. What's about to happen on the bottom? The reason we multiplied by that minor denominator is so it would cancel with that denominator there, the x. So all we have is 3x over 3. What's that going to reduce to? Just an x. The 3's cancel. So f composed with g of x reduced just to x. Odds favor, if you were a gambling sort of person and you were running out of time and this was on the test, you'd be safe. Your safest bet would be to assume what? What do you think is going to happen with g composed with f? I think it's going to equal x too. Most of the time, if it equals x in one way, it'll equal x the other way as well.
80%.
80%.
Yeah, so better odds than any sort of gambling game. 80% chance guess it's going to equal x, but we don't have to guess. We can actually.
Oh, wait a minute.
Shoot.
Remember what I would do?
Yeah, you got to restate.
I'd restate them, remember? Because of all those arrows making such a mess, I'd rewrite them each time. So now, g composed with f. G composed with f. That means you're taking f and plugging it into g. You're taking f and you're plugging it in to g. Did y'all follow that? We're taking f, plugging it into g. So we're going to we have that 3 over. We're going to replace the x with that 3 over x minus 8. And we still have what else? That plus 8 that's stuck on the side.
See, you can't just cancel the 3's. Like right up here, you couldn't just immediately cancel the 3 without, like right here. And then, so you'd have what? Nothing over x remaining. You got to do that multiplying first.
Let's look. We have a compound fraction here. What's my minor denominator? Be careful.
What's
the x minus 8 is the minor denominator. There's the major denominator. The
The x minus 8 is the minor denominator, so I'm going to multiply above and below by x minus 8. Don't worry, it's about to work out really nice. And then you can cancel the x minus 8s there. Can you cancel the 3's now? Yes, you could cancel the 3's. I'm going to rewrite it for a moment, just to show. Don't decide to distribute through the 3. Remember, you need the stuff in factored form if you're canceling. Here, it's in a factored form. You have it as a product on top. So you can cancel the 3's, and that leaves us an x minus 8 plus 8, which reduces just to x. So, are these functions inverses? It was a yes-no question. Are they inverses? Yes, they are inverses. Go ahead and pass the hand sheet. Are inverses. Any questions? Next. Any questions? Fog x equals x, more than likely golf x will. But, it's okay. It's okay if they do that. But it'd be bad form if you did. It'd be bad teaching if I just said, oh, it's probably going to be x. Let's just guess. Okay. Here's another one. No, this is different. Oh, different. Okay, yes. Okay, you need to talk. If we have two equations and we're wondering, are those things inverses? We can test. Just find their composition. See if they reduce to x. If so, then great, they're inverses. If not everything cancels out, if you're left with something other than just an x, then they're not inverses. So the natural question is, how do you find an inverse? Okay. It's easy when you're given ordered pairs. You just switch. Yeah, but ordered pairs, it's easy, okay? What about how to find the inverse of a one-to-one function equation? How to find the inverse of a one-to-one function equation. You didn't mention the equations. They basically work with equations. They've been working with equations all semester. Inverse of a one-to-one function equation. The first thing you're going to have to do is verify that the function is one-to-one. You don't want to bother finding an inverse if the function is not one-to-one. So I'll say verify f is one-to-one. No, not a question mark. And maybe I should, here's how you can look and decide if it's one-to-one or not, just by looking at the equation. Like looking at this one, it's sort of hard to decide. Well, I've given them everything they need to know about it. We said. Look at this thing here. Switch back. Look at this quadratic function. We know a quadratic function is any function in the form y or f of x is equal to ax squared plus bx plus c. One of those terms is responsible for these repeated y values. There's one of those terms that's making whether you plug in a positive or a negative, you get the same result in that event. Which term does that here? Whether you plug in a positive 5 or a negative 5, you're going to get the same thing. It's the thing that creates imaginary numbers. It's the thing that people like that really you have no reason to like. The odd ones are a lot better. Those even exponents. Think about when you raise a number to an even exponent. Whether it's you plug in a positive 5 or a negative 5, when you square it, you're going to get a positive result.
It's those even exponents that cause functions not to be one-to-one. Even exponents, you should expect the equation to be not one-to-one. There is something else that could appear that we've worked with that would not give us a one-to-one result. It sort of looks like a parabola, the graph, if I remember correctly. We saw something else that it didn't matter if the stuff was positive or negative on the inside. Once you did perform the operation that was there, it turned out to be positive. What graph has a graph? What equation has a graph that's similar to U but has a point down there?
The V-shaped graph.
The absolute value graphs?
Yeah. So how can you look at problem number 11 and say, that's one-to-one? Well, write it out, Tim.
Verify f is one-to-one. That means there should be no even exponents in the equation.
And no absolute value bars.
If you're looking at an equation, to verify that an equation is one-to-one, you're just convincing yourself. There's no work. When I look at that problem that Tony's showing there, there's no even exponents. If you plug in a 5 and a -5, you're going to get different numbers. I'm able to convince myself, yes, that is one-to-one. So switch back to my paper. So the first thing we'll do is verify that f is one-to-one. If it's not one-to-one, we're not going to waste time finding the inverse. The second step, just tell me in words, what does an inverse do?
And I defined inverse the first time, not the formal definition.
It's formed by switching the x and y values. So second step, I'm going to say swap x and y. Wherever you have an x, you're going to write a y. Wherever you have a y, you'll write an x. At that point, you have an equation that's a form of the inverse, but they're going to want you to write that inverse using inverse function notation. So you'll need to solve for y, solve for the new y, and then replace y with that inverse function notation. F inverse of x. You won't have to type that f inverse of x notation because my lab will give it to you. Really, once you solve for y, whatever's on the other side of the equation, that's your answer. Let's look back at that problem number, was it 10? 11. F of x is equal to 2 over x plus 1. Is this function one-to-one? If so, they want us to find a formula for its inverse. Is it one-to-one? Yes, there's no even exponents, there's no absolute value, there's nothing that would yield a repeated y value. So yes, it's one-to-one. Okay. So now they want us to find the inverse. And notice how they've written it. They've already typed in out the f inverse of x. All you're going to need is to solve for y, and whatever's on the other side, that'll give it to you. You have to swap the variables too. Switch to my paper. So we verified that the function is one-to-one. Now we're going to swap x and y. Wait a minute. I don't even see the letter y here. What's acting like y? What's acting like y in this original function? I know that's x. No.
I have something written here that represents y. That f of x, that's just a fancy way of saying y. So f of x is y. You're going to swap the variables. Y becomes x. X becomes y. Any questions on my logic? Your f of x is a fancy way of saying y. So y became x. X became y. Now we need to solve for y. I think I'll set this up as a proportion. That x I can think of as x over 1. And when you have a proportion, you can cross multiply. Y'all remember doing that? X times y plus 1. What are we going to have to do there to multiply x by y plus 1? Distribute to give you an xy plus x times 1 is just x. Gosh, this is working out nicely. What have we got on the right side? 2 times 1 is 2.
So you're trying to isolate the y now.
We're trying to solve for y. Well, there's only one y term. We'll get that y term together and then divide by x. We'll get that y term by itself and then we'll divide by x. But before we do that, what do we have to do with that plus x? Subtract x to get xy equals 2 minus x. And then divide by x. I'm getting down real low. That gives us y equals 2 minus x all over x. And this stuff here is the final answer. Once you solve for y, the step on the other side is what you're going to be typing in. They've already given you that f inverse of x. You don't have to, I guess, if you wanted to write the whole thing out, there it is. But the answer is the stuff on the other side. Tony, type that in.
2 minus x all over x.
I'd use the fraction hot button. On top, I have a 2 minus x. Clicking down on the bottom, I have an x, and check. Any questions there?
Swap x and y, solve for y.
And then the step on the other side of y is the answer. Let's do another one. This is number 12. They give us the function f of x is equal to x cubed minus 9.
I remember one semester the student saying, this is not one-to-one because of the exponent.
I didn't say that.
Said, no, that's not what I said.
I said no even exponents.
Okay.
When if you tried plugging in, say, 2 and negative 2, with that odd exponent, would you expect to get the same number back? Odd exponents don't change signs. If you plug in a positive number for x, when you cube it, it's positive. If you plug in a negative, negative times negative times negative, it stays negative. The sign doesn't change. So that is odd. Reminds me of those radical equations. Remember, you had to check the answer on the ones that had the even indices, square roots and fourth roots. But we would have said back then that odd powers don't change signs, so you don't have to check those equations. That's odd, so this thing is one-to-one.
Is it clear why we're saying it is one-to-one? It's not no exponents. It's no even exponents.
And so now we're going to...
Wait, is it one-to-one?
Yes. And now,
So we can find the inverse now. Remember, everywhere you have a y, you write an x. Everywhere you have an x, you write a y. And realize that that f of x is just a fancy way of saying what letter. So we have a y on the left side, it becomes an x. The x on the right side becomes a y. And we need to solve for y.
there's only one correct step to get the y by itself. I mean, to solve for y.
Two correct steps.
No, the first
With the
step.
fewest, in the fewest steps. We're trying to get y by itself. What should we do first? Add the 9 to give x plus 9 is equal to y cubed. And now, how do we get rid of that cube? What will undo that cubing effect?
What cancels out a cube? A cube. There's a word I'm looking for after the word cube.
Okay, let's go back. Let's go back to the.
I'm doing a.
I think you just need to keep your mouth shut.
I'm going to keep my mouth shut.
Okay, you're going to keep his mouth shut. Good. Let's see. Oh, don't you love having all this stuff written out like this? Let's see. There it is. What undoes a cube root?
Like a square root undoes a square.
Okay, so. Oh, wait a minute. I was going the wrong way. I answered what undoes a cube root. What undoes a cube? Well, a cube root. I was going the wrong direction. A cube root. We can't use this terminology. We weren't able to use this terminology back when we were solving those radical equations, but now I can say it. The cubing function and the cube root function are inverses. When they're performed consecutively, they cancel out, leaving you, in this case, just the letter y, to give us y equals the cube root of x plus 9. And our inverse function is the step on the other side of y. We're using inverse functions to find the inverse of the given function. The cubing function and the cube root function are inverses. The way they're performed consecutively, they cancel each other out. That's the basic definition of an inverse function. Any questions there? So I guess if you want me to finish it off, I can write it like this. F inverse of x is equal to the cube root of x plus 9. But invariably when I do that, people start typing that into the box also. The answer is the step on the other side of y. They've already given you that F inverse of x notation on my lab. Did you type in the answer?
I'm going to, and I'm going to give the students a little word of warning. On one of the meetings, my hiring committee meetings, one of the faculty members there got really upset about the word cancel. He raised his voice so much. Why didn't y'all ever tell us to dim the lights? That's what's so weird.
I dimmed the lights.
Oh, you did? Oh, okay.
Didn't I dim the lights?
Oh,
I didn't dim them.
so bright to me.
Maybe I forgot to dim
he got really emotional and talked so loud. So be careful using the word cancel around some
Formally,
teachers.
the definition of cancel is a multiplication and division operation. What I did right there, dividing, that was the cancellation property. There's an algebraic property, the cancellation property. That's what I just did. The way when it's multiplied, you can divide and cancel out. That's really canceling. Anything else, addition and subtraction, the 8 minus 8 a moment ago, technically that wasn't canceling. in the
That's
algebraic
adding to give
definition,
zero.
but in the English definition, yeah, that would.
Yeah,
And I
well.
used to be one of those people years ago. I would never say cancel.
No, don't say cancel
They
unless it's...
subtract to zero or
But in
or-
the English language definition of cancel, yeah, when you have 8 plus a negative 8, or negative 8 plus 8, okay? So I'm just thinking of that, because I was sort of shocked.
Did you type in the answer?
Didn't I? You took the mouse.
Is there another one?
No.
I
That's
think
it.
no.
Number 13.
Oh,
There's
the
a review. Circle. Do you remember that completing this? Y'all want to review that? Tim, do
Y'all
you want
remember
to do
completing
that?
the square? Y'all want to review one of those?
You want
Yes.
Tim to do 13?
Or do you want to go?
It's just an hour and 5 minutes. This week I'll be playing your part and say, we have enough time, let's do more than we need. Is that more? Okay? We have time. Only an hour and 5 minutes. And this is something that, sort of takes a little bit to jog your memory. You got to get that circle written in that.
Switch. You have to get that thing written in center radius form. Remember, center radius form looks like this: x something squared plus y something squared equals a number, a positive number if it's going to be a circle. Was this on the midterm? I don't think so. This is the first assignment that's after the midterm. Do I remember what we'd do? We'd look and we'd see, the leading coefficients are 1. That's good. And then we'd group the x terms together. So we have an x squared minus 6x plus, skip some space. We group the y terms together. Is this looking familiar? Skip some space. And on the right hand side, we already have the constant there, -9. But we have 2 blanks that we're going to be adding into, aren't we?
This is so terrible. That blue and black look so much alike.
Yeah, I know. Okay.
Do I remember how to find the number that goes in the blank? What are we
I'll
gonna
get
do?
us started. You take that number there. Don't need to worry about the negative. Just take that number. The first thing we do is we divide it by 2. 6 divided by 2 is 3. This process was called completing the square. What would we do with that 3? Square it, okay. 3 squared is 9. So we put a plus 9 and a plus 9.
Do the same.
Now do the same thing for the y's. What number am I going to put right there? 1, I agree. You would have taken 2. You have to divide it by 2. That gives you 1. And then you square 1. 1 times 1 is still 1. So you add 1 to both sides. And then you're able to factor these things.
It should be factored with a square, like you have right here.
So that's variable. We had a little pattern here that when we're factoring, it's not like trial and error or anything. We had a pattern. Variable, sign. What sign am I going to put there? That minus is that first sign. So it's the variable, sign, and then what number is going to go here?
It's a number you can square to get a 9.
3. Okay. I would say variable, sign, half of that number. That's the little pattern that I would say. Whatever the first letter is, whatever the first sign is, whatever half of that number was. Here, you tell me what's going to go inside these parentheses. Y, I agree. Sign,
Plus
number, 1. Variable,
sign, half of that number. And over here I have a negative 9 plus 9, that's gone. What are we left with? Just a 1. That's a positive number on the right, so we do have a circle. What's the center of the circle? Oh, notice we got it in the form we needed. The parentheses with the x squared plus the parentheses with the y squared equals a positive number. Who remembers how we find the center and radius? We have
One of those little sayings will be there in the nursing home saying. Change the sign,
change sign,
square
take
root.
the square root. Change sign. Do y'all remember doing this? Take the square root. So the center is at the point 3, negative 1. The radius is 1. Do y'all remember doing that? Yes? I just keep asking y'all that until you answer yes. Okay?
Teaching tips.
So that would be response B. It's a circle.
Gotta put those parentheses. 3,
Comma, negative 1. Right, parentheses. And then the radius is 1.
Now, if we had wound up with an imaginary radius, then you would have said the graph is non-existent.
Look back here.
If there had been a radius of 0, it would have been a point.
If it's a positive number, it's a circle. But if this thing was negative, then it's nothing. No graph.
You don't think that look negative of yours looks like a fraction bar? Maybe you could write out any G. Is that perfect penmanship?
Negative, no graph. And if it's 0 on the right-hand side, we said that it was just an ordered pair. It's the center point.
So it's just 1 point.
And nothing else. Any questions there? Oh, and a cut point problem.
14 and 15 are cut points. You want me to do one of those? Which one you want me to do? Or he can do?
No, I'll let Tony do it.
Oh, you're getting lazy, Tim. Which one you want me to do? 15? Okay.
No.
Once I've done 15, I'll ask if you want me to do 14 also. What the heck? I can't believe we have so much extra time. Okay, number 15. Absolute value of x squared plus 5x minus 10 is greater than 4. Did I miscopy it, Tim?
No.
Okay. Anytime you're solving an inequality, you're going to be using the cut point method. Here, there's no denominator cut points.
That's sort of blurry, this blue. Put that away there.
What do y'all think? Is that blue blurry? To me, it looks a little blurry. No?
Well, it's my 62-year-old eyes, I suppose, that are making it blurry.
So with the cut point method, we have to have those solution cut points and denominator cut points. Well, first of all, there's no denominator cut points. There's no denominator. So to solve an absolute value equation,
What is he going to do first?
He's going to do equal negative.
Okay, you go equal positive, equal negative. And these are going to get me the solution cut points. Will there be, when I label them on the number line, will they be open or closed?
Open.
Open circles, So let me see. I'm going to Draw a line. Okay. To solve this quadratic equation, we need a 0 on one side. So I'll just move that 4 over.
Why is it flashing so?
And I'd have x squared plus 5x, subtracting 4 from both sides. Is that going to be a minus 14? And it's a quadratic equation because of the x squared, so that means you got to either factor or use the quadratic formula. I'm going to factor it.
It's a simple trinomial. Notice the leading coefficient is 1. So all you can have is x times x.
1 times 14 or 2 times 7. Are those the only possibilities? 2 times 7. Now, I need a negative 14, so that means it's going to have to be a positive and a minus. How do I make them put the signs in order to get a positive 5? Negative 2 and positive 7. Then set each one of these to 0. My first cut point is positive 2. What's my other cut point? Negative 7. Now I'll come over here and do the same thing. I'll move the 4 over by adding 4. So I have x squared plus 5x. Adding 4, negative 10 plus 4. What am I going to have up right here? Negative 6. So x and x. 1 time. Oh, this is tricky.
Yeah. I like
1
that.
times 6 or 2 times 3. At first
What
you
do we
might
know
think-
about the signs?
Yeah.
I'd write
it's
in a
gonna-
plus and a minus.
Okay.
I'd write it in right there.
So these two numbers I choose are going to have to subtract to give the middle term. Okay? So I'll ask again. 2 times 3 or 1 times 6? What am I going to use? 1 times 6. How do I arrange them? 6 is positive. 1 negative. And then I set each factor to 0. And we get x equals negative 6 and positive 1.
Hey, I have a question. Can we assume an alternating pattern on this problem? Or we have to check every interval on the number line? You can assume an alternating pattern. Notice when we factored, every factor is different. We didn't have x minus 2 times x minus 2. You didn't have x plus 6 times x plus 6. There's no repeated factors, so you can assume an alternating pattern. And that's important because there's 5 intervals here. Those 4 cut points are giving us 5 different intervals.
1, 2, 3. I put my 4 marks on there. Now let's put these numbers in numerical order. We said that they'd have an open circle. So which one is closest to negative infinity? Negative 7. And then negative 6. 1 and 2. Normally I test to 0, but where does 0 lie? Okay, always between a negative and a positive. So this is the interval between negative 6 and 1 that contains 0. So that's the interval I'm testing. I'll either cross it out or shade it. And then I'll alternate from there. So let me plug it in. Testing a 0. Okay, so plugging a 0 in here. Have 0 plus 5 times 0 is 0 minus 10. Be careful. Inside the absolute value bars, we just have what? A negative 10?
True or false?
You've got to take the absolute value.
People will say false, but they're forgetting to take the absolute value.
What's the absolute value of negative 10? Positive 10. So here's what we're using to decide between true and false. Positive 10 is greater than 4. True or true? So let me see if I can. So shade. What are the rest of them going to look like? Well, if it alternates, false, true, false, true. And I'll write it out in interval notation now. The shaded intervals. Don't write the crossed out ones. So it's parentheses, negative infinity, comma, negative 7, close parentheses.
And what do you put next? That U from the toolbar. Okay, good.
Negative 6 to 1, union 2 to infinity.
Okay, so
Type it all
left
in.
parentheses, negative infinity, comma, negative 7, right parenthesis, union,
Negative 6 to 1,
union,
2 to infinity. Okay. That sort of jog you. Oh, wait, we're not finished.
through. They're not using the open circles. They're using brackets and parentheses. Well, it's not the brackets. That would have been closed circles. So it's either B or C. Which one?
No, C.
C.
I said the wrong thing. You know what?
Why not?
Yeah.
Why not? Let's do this last one.
If you have to go, I won't take it personally. Okay?
Okay, good, because I got to go.
X minus 13 over X minus 16 is greater than 3. Now, this one has a denominator, so we're going to have to do both the solution cut point and the denominator cut point. So let's see, I'll do solution cut point first. With the solution, oh wait, I'm going to start writing and writing. There. With the solution cut point, you're solving the solution, which means set it equal, and I'm going to solve this just by cross multiplying. Oh, I set it up as a proportion in case you couldn't tell, setting it as 3 over 1. So let's see, we'd have what, a 3x minus 48 equals x minus 13. So let's see. Putting these little arrows here, is that sort of hinting at what I'm about to do? I'm going to subtract 1x, so 3x minus 1x is 2x. And what are we going to have on the right? I'm adding 48. So 48 minus 13, is that going to be a 35? Okay. One thing left to do, which is what? Divide by 2. Ooh, 35 over 2. We're going to have to plot that on a number line, so we might want to, we might have to think of it as a decimal number. 35 divided by 2 would be what decimal number?
17.5.
Okay, I'm going to write the 17.5 in this invisible ink here because, but that way, okay, I'm just thinking 17.5. I won't use 17.5 when I'm typing in an answer. So that was the solution cut point. There's another cut point we have to find on this one that we didn't have to find on 15. And what's that? That denominator cut point, we say denominator can't be 0. X can't be 16. So I will draw a number line. I specifically used the invisible ink to write the 17.5 there, okay?
Good.
Because I know you would be upset.
No, I'm not upset. It's just, accessibility issues.
Yeah. Okay, so wait, which number goes closer to negative infinity? Which cut point, the 35 over 2 or 16? 16. Hey, I didn't ask y'all about the circles, open or closed? Open. Denominator's always open. Oops. I'm going to say always open. You don't have to look at anything. For solution, you look at the symbol and it's open. Because there's not an equal sign. I'm going to test 0. Where does 0 lie? Between negative and positive. So plugging in a 0. We have 0 minus 3.
13.
Oh, I'm sorry. 0 minus 13 would be just a negative 13. And what about on the bottom? 0 minus 16, negative 16.
True or false?
A negative over negative is positive, but 13 over 16, that's less than 1, isn't it? So what are y'all saying? False. Oops. False. True. False. So parentheses, 16, comma, 35 over 2. Okay.
16, comma, 35 over 2. Get out of that denominator before you close your parentheses.
And I think we've done everything.
Oh.
Okay. Any questions on this? The last 3 problems were just reviewing old stuff, okay? The new stuff was the inverse functions and one-to-one.
Okay. Oh, wait.
Uh-oh, what's happening?
I'm going to stop recording.